Well, without further ado, Hadley.
Thank you. So tonight we're going to have a sort of a double-header act. First I'm going to talk a little bit about a package I've been working on, dplyr, and then Joe's going to show you some cool, shiny stuff. So the motivation for a lot of my work is thinking about how can we make data analysis faster and easier and more fun. And to think about that, I think it's really useful to think about what are the bottlenecks when you do a data analysis. And I think the cost is really a combination of two things, a cognitive aspect and a computational aspect. So you have to first think about what you want to do, and then the computer's got to go away and do it. And if you're thinking about how you can make data analysis faster, you need to think about both of those aspects. And in fact, I think we can be even a little bit more precise with this, because I think there's some overlap. So once you've figured out what you want to do with the data analysis, the next thing you have to do is describe it sufficiently precisely that a computer can understand it, or in other words, you have to program it. Then once you've programmed it, then the computer can go away and do it, and hopefully it will do it in an efficient way that doesn't take too much time. So if you're thinking about the entire time course of a data analysis, and you want to make it fast, you've got to think about all of these aspects. And I think one thing that's nice about this breakdown is it gives sort of a nice definition of big data versus small data. And small data is where cognition dominates computation. So when you're working with small data, you spend a lot of time thinking about it relative to the amount of time you spend computing on it. Whereas with big data, obviously you spend more time thinking about it, but as a proportion of the total amount of time, it's relatively small. Even once you've figured out what question you want to ask and how to ask it, the computation time is still going to take a large proportion. So what I've been working on to make all of these parts easier in R is a new package called dplyr, which is the next iteration of the plyr package. So first I want to talk about the side of it which makes it easy to think about data analysis and then to describe that programmatically, and then I'll talk a little bit about some of the ways that dplyr makes it fast to compute as well. So the key insight I had is that there really are only a few key data manipulation verbs, and it really shouldn't matter where your data lives when you're expressing those operations. So I think there's basically 5 key verbs. You want to be able to select columns, you want to be able to filter rows, you want to be able to add new columns that are transformations of existing columns, you want to be able to summarize multiple values down to a single value, and you also want to be able to arrange the rows. So when you combine these 5 verbs with a group by operator, I claim, without any evidence, unfortunately, that this will solve the majority of your data manipulation problems. So just this framework kind of helps you think about a data manipulation problem, because when you've got a problem now you can say, well, which of these 5 things do I need to do, or you may need to use more than one of them, and how can I combine them within groups to solve the problem that I'm trying to solve. So I'm going to show you a little example of using dplyr, and unfortunately there's a reason that you don't program in Keynote, and I've made a small typo there in the first line. But I'm going to load in a large data set. So how many of you are familiar with read RDS? So the read RDS functions, read RDS and save RDS are really useful ways of saving a single R object to a file on disk in a way that can be loaded as quickly as possible in R. So these are they're similar to save and load, but instead of saving multiple objects, they save a single object to a single file. So this data is in fact every single package downloaded from the RStudio CRAN mirror since the beginning of this year. There's about 21 million observations in total and 10 variables. So there's one annoying little bug in R that if you try and just print these large objects, which are in fact data frames with some special properties, if you just try and print them implicitly, it takes a very long time to print. So it's much faster to print them explicitly by calling print, unfortunately. And then dplyr tries to do the sensible thing. dplyr knows you have lots of data. It's not going to show you the first 10,000 rows. It knows that is provably useless. So it's just going to show you the first 10 rows and all of the columns that will fit on one screen. and then it will give you a concise summary of the remaining columns. So the idea is you can easily look at your data, but it's not going to overwhelm you. So one of the principles of dplyr is you shouldn't accidentally do something that's going to take a long time to compute. You should do that deliberately. So whenever I've been working with these large data frames in R, often I'll accidentally print one, and then you have to like try and kill R basically because the print statement is incredibly inefficient and doesn't even let you break out of it. So this dplyr saves you from that a little bit. So also it does some nice things like when you're dealing with millions of rows, it's nice to see a few commas to help you understand. And then I've cached this object, which is a table df, which is a special type of data frame. Normally you'd create that with a table df function, but here I've cached that already. So I'm going to show you a quick example of a dplyr analysis. So I've loaded this data set already. It's about 260 megabytes on disk, 1.5 gigabytes in memory, so it's not like a huge data set, but it's pretty sizable. So what I'm going to do is say I want to look at packages. So the first thing I'm going to do with dplyr is say kind of my unit of analysis is the package. And you'll notice this takes a few seconds. What this is basically doing is building up some indices so that we can do subsequent operations very quickly. So if we look at this, and again, I'm going to print that explicitly. Basically, this looks exactly the same as before, except it now tells us that we're grouping by package. So basically what we're doing here is we're saying our unit of analysis is the package for this question we want to ask. Next, what I'm going to do is I'm going to summarize each package with the number of times it was downloaded. So the n function is just a shortcut for a count of how many observations are on this group. And when I run this, you'll see it runs very, very quickly, even though it has to iterate over 21 million observations in order to compute them. So we can look at that just to prove that it has actually done something. I'm not lying. So in that time course, there were 5,851 packages downloaded, which now that I look at it, is kind of surprising given that there are only 5,000 packages available on CRAN. That is rather interesting. But probably I want to look at the most downloaded packages. So I don't just want to look at the raw data, I want to arrange it in terms of, I want to arrange it in order, descending order of the number of times it was downloaded. And hopefully this doesn't look too self-serving. So we could, of course, just look at the top 10 using head. Or another way of expressing the same thing, one thing that's a little bit worrying about using sorting and then just taking the first 10 rows is what happens if the 10th is tied. How do we want to deal with that? So it might be better to use a function that knows how to deal with ties. So here, instead of arranging and then looking at the head, I'm going to filter it using the rank function on the descending values of n, and I'm going to find all of the packages with a rank less than or equal to 10, so the top 10 packages. So just another way of expressing a similar idea that's a little bit more sensitive to ties, which actually doesn't matter in this case, but does in general. So the equivalent plyr code takes about 10 minutes to run. So generally dplyr is 100 to about 10,000 times faster than plyr, and it's pretty close to data table in terms of performance. So there's some operations that dplyr is faster at, there are some operations that data table is faster at, but I think overall it's about a tie currently. Now the other thing that I think is sort of interesting about the way that dplyr has been written, and I'm still not sure I'm in love with this style, but you can sort of express things in a, like, think of a grammar of data manipulation in a similar way to ggplot2 being a grammar of graphics, where you iteratively build up a data manipulation. So here we can sort of read this like a sentence. We start with the logs, we group by packages, we summarize each group, looking at the number of observations. We then arrange it in descending order of n, and then we look at the first 20 observations. So this %.% function is something that I wrote. It basically takes x %.f of y, and it basically does a little bit of R magic to make it look like you've called x and then y. So it's a way. So normally when you write out operations like this, they become deeply nested, and you have to read from the inside out, which means that you have to read from right to left, which is not very natural if you're an English speaker. So this allows you to flip it around, read it from left to right, just like you're doing things step by step by step.
I'm going to Peter School.
And I should just show you that too here. So I'm just going to save the top 10 packages into a variable which I've created by stringing together those 5 steps. So I think this is really important, that just like ggplot2, when you create a plot, you build a complicated plot through a series of simple steps. In dplyr, you perform a complicated data manipulation by stringing together a series of very simple operations. Now, as well as verbs that work with single tables, and pretty much any real data analysis, you have multiple tables of data. And so it's useful to think about what are the verbs that allow us to combine multiple tables. And those are basically the joins of SQL. So there are lots of joins in SQL. I think there are 4 that are most important. The left join, where you have all of the rows of X and the matching rows of Y. The inner join, where you have the matching rows of X and Y. And then 2 other joins that I only recently learned about, the semi-join and the anti-join. So the semi-join says, take all of the rows of X. So it says, give me only the rows of X that have a match in Y, but don't give me any of the columns in Y. The anti-join is the opposite of that. It says, give me all of the rows in X that don't have a match in Y. So semi-join is a really useful tool when we have selected, say, the top 10 packages, and now we'd like to see how have the top 10 packages varied in downloads over time. So what I can do is a semi-join. I'm going to take the packages object. Actually, it's probably a little more sensible to think about taking the logs object, where each row is an individual download. I'm going to join that with a top 10 data frame where each row is a package. This is going to give me all of the downloads for the packages that were in the top 10. So I think this is a really useful tool for selecting data. It's kind of like a match or a subset that you can match based on multiple variables easily, not just one. Now what I want to do is look at the number of downloads daily for each of those packages. So I take my data frame, I'm going to group it by the package and the date. This time I'm going to summarize it by 2 things, not just the count, but also the number of unique IPs that have downloaded that package that day. So you might be worried, for example, that I've been inflating these numbers by downloading the packages many times.
No, you just use different IP addresses.
Wow.
That also works against you, because don't colleges have the unique one unique?
Yeah, so looking at unique IPs is a little bit perilous because there can be situations where one person uses multiple IPs, and in other situations a single IP will represent multiple people. And there's certainly cases where we have IP addresses that have downloaded like 40,000 packages in a day, which is clearly unusual. So you can see this data frame. We have the package column, the date column, the number of package downloads, and the number of unique identifiers. Now, of course, just looking at the raw data isn't very useful. Typically, we might use some kind of plotting package to look at that. And so the thing that's neat about, I think, about working with large data is as long as you can summarize the data quickly, you can use any existing plotting tool. So generally in a visualization, the bottleneck is the number of pixels that you have available on the screen. And so you don't want to display every single observation, you want to display a useful summary. So this plot isn't terribly useful. The main thing it reveals is that people do not download R packages on the weekend. So rather than displaying the raw data, what I'm going to do is use a geom smooth so we can see the overall trends. So you can see this sort of, it looks like there's an inflection point around August. But overall, it seems roughly that the ranks in the top 10 are staying pretty constant. Now, it's a little bit hard to interpret this data because this is the data just from the downloads of the RStudio CRAN mirror. So it may be, for some reason, a whole lot of people switched to using RStudio in August. And of course, that probably represents the start of the school year and people downloading new packages for their classes. We do see a pretty strong uptick in the number of package downloads and RStudio downloads when the school year does start. We can look at the number of unique IPs. I think the main thing that this plot reveals is that whoever wrote the script to calculate these IP IDs screwed it up, and unfortunately that was me. But again, if we add a little bit of smoothing, maybe we can see a bit more of a story, although we know all of this is spurious because of a data quality problem. So one interesting thing that I discovered in the course of doing this, and that's the RStudio CRAN mirror has served it served 20 million package downloads. That's about 16 terabytes of data, which is pretty impressive, I think. So that's the sort of the cognitive side, thinking about what are the key verbs for data manipulation, how can you express them in code. What I want to talk about now is a bit more about the computational side. How do we make this as fast as possible? And the key insight here is that when you've got big data, you don't want to move it around. You want to leave the data where it is, and you want to move the computation to where the data lies. And so one of the key ideas underlying the dplyr package is that you should be able to work with the data however it's stored. So not only does dplyr support local sources like data frames or data tables, there's also an experimental sort of OLAP data cube and a multi-dimensional array. But you can also work with data when it lives in a database. So currently dplyr supports Postgres. So the idea is, like, if we're going to move the computation of the data, well, we're going to have to translate what we want to do from R to SQL. Now this sounds like a bit of a crazy idea, but I think it's not too insane, and we can make it work pretty reliably. And so in dplyr, there's basically two steps. We need to think about how do we translate these higher level data manipulation verbs to SQL, and then how do we convert the lower level expressions used in those. And so here I'm going to use a slightly different data set. This is the H-flights data set, which contains all flights departing Houston in 2008. It's not particularly huge, but it's easy for me to put into a database. So you'll notice here I'm creating a link to the database, and then all the other code looks exactly like the code I was using before. It doesn't matter that the data is in a database rather than being in a local data frame. So again, I'm going to group it this time by tail number, which is going to give me a unit of analysis, that's the plane. Then what I'm going to do is mutate the planes. I'm going to add a new column within each plane. I want to rank them according to how late they arrived. So I want ones with low ranks to have had high delays. So if I was to write this out in SQL, it's going to look something like this: select star, comma, rank over partition by tail number, order by arrival, delay, descending as rank from H flights. So this thing here is called a window function. It's available in relatively few SQL databases currently, but both Postgres and Google's BigQuery supports it. It's in, I think, Impala. It's planned for Impala 2. Redshift supports it, and so on. So I think window functions are really, really important if your database is going to support analytic questions. So here we needed to answer a relatively simple request. We can explain this pretty easily. For each plane, rank all of the flights according to how delayed they were. But that's relatively harder to express in SQL. Similarly, for a grouped filter, the same thing. We've still got these planes. Now for each plane, I just want to find the worst flight or the flight where the arrival delay is equal to the maximum arrival delay. This generates an even more complicated SQL query for two reasons. So first of all, window functions can't be used in where statements or having statements. So we have to put them inside of a subquery. And then the other problem is SQL has no way of saying, give me all of the columns except this column. And because we've added a new temporary column in here, we don't want to include that in the output. So we've got to manually list all of the other columns. So at a pretty high level, dplyr maps the different data manipulation verbs to different components of a select. So for example, if you're going to do a summarize instead, that would use aggregate functions in the group by clause. Now, as well as translating these high-level verbs, we need to translate the lower-level expressions inside of them. And here we can do it, by and large, pretty automatically, because at this level, the expressions we use to subset rows or to create new variables look pretty similar in almost any programming language. Now, we can't translate things perfectly because obviously there are lots of things that you can do in R that you can't do in SQL, and functions, for example, like the mean function in R does 2 passes over the data so it could be more numerically accurate. Databases don't care about that. The mean function also has a trim argument which lets you throw away the tails of the data. Databases obviously don't have that. But by and large, I think we can translate the intent of functions, simple functions, from R to SQL. So I'm going to show a little bit of the translation here using the translate SQL function. Now, one of the things that's interesting about this dialect of SQL is that you need to escape variable names with double quotes. So this looks a little bit strange if you're an R programmer because that looks like a string, but that's how many SQL databases escape variable names. And escaping variable names is really important because you don't want to accidentally do some sort of SQL injection attack where you accidentally do something horrible to your database. The other thing that's interesting with SQL is it has a different convention for when something is an integer versus a real number. In SQL, if you have a bare number 1, it's treated as an integer. In R, it's treated as a floating point number. In R, if you want a number to be an integer, you have to put a capital L after it because, of course, capital L stands for integer. Now here's another, I think this example demonstrates why you don't want to be constantly switching between R and SQL, because R and SQL in many ways are so incredibly similar, but they have a few differences that are really frustrating if you have to switch between them. So for example, here we're saying the destination is IAD or it's DCA. When we translate that to SQL, well, strings in SQL use single quotes. We write out the function OR, and then we use single equals instead of double equals. Right? These are the little things that trip you up if you're writing R 1 second and SQL the next. Then finally, it's smart enough to be able to interpolate local variables, local objects. So here we've defined the DC variable to contain a vector IAD and DCA. And when we say the destination should be in DCA, it can figure out that that's local and include that string, include that vector in the string that's sent to SQL. So my thesis is, well, certainly on a laptop using dplyr, you can do interactive analysis on over 10 million observations in R. I think if you have a high memory server, for example, on EC2, you can now get a server with 240 gigabytes of memory, and it only costs about $3.50 an hour. If you do that, and if tools in R can take advantage of parallelization, I think you can work interactively with hundreds of millions or billions of rows in R. So while R is fundamentally limited to work with in-memory data, what in-memory data means today is very different to what it meant even a few years ago. So if you want to try it out, you're very welcome to. It's currently available only on GitHub. It will hopefully be available on CRAN, all going well, early in the new year. So if you'd like to learn more, Google for dplyr, that will get you to the GitHub site. There are a number of vignettes in the package which help explain how you can use it, how the database connections work, and so on in more detail. And if you'd like a copy of this presentation, it's available at that link. Thank you.
Now, I use the dplyr.
Mhm.
Is this different than a dplyr? Or
So ddplyr is a function, and plyr, I should have explained, the reason why this is called dplyr is this is sort of an iteration of plyr that focuses only on data frames. So after creating plyr, which allows you to easily work with arrays and lists and other things and data frames, I realized like 90% of the time the functions I reached for from plyr were ddplyr, ldplyr, and dlplyr. And so with that more limited scope, you can make functions that work much more quickly than plyr because they're only working with data frames in a certain way. So dplyr is sort of a rethinking of what are the key tools for data manipulation focused around data frames and data frame-like objects.
So if we've had some experience with data table, what does this do better than data table? What solution is this trying to provide that data table isn't? It seems like one is interfacing with databases,
Yeah.
but is there something else that's really...
So I think there are two philosophical differences between dplyr and data table. Apart from the sort of the minor differences, like I think dplyr has a slightly broader scope in terms of it wants to help you work with databases as well. But there are two main philosophical differences. First of all, data in dplyr is always immutable. You can never pass a dplyr. Dplyr things are just data frames. They behave exactly the same way as every other object in R, whereas data tables are mutable. So that's a major philosophical difference, and some people will like their data mutable and other people like it immutable. The other difference is sort of a difference of philosophy and functions. dplyr has lots of little simple functions that each basically do one very specific thing. Data table has one function that does pretty much everything. So while the goals are the same, the way you express those goals are very, very different between those two. And so I think, data table does solves the set of problems that both data table and dplyr solve are fairly large, but there are also problems that dplyr solves that data table doesn't, and vice versa.
Can you speak a little bit about the integration with BigQuery there? It's kind of a standout because it's not an RDBMS.
Yeah, so the thing that's interesting is that basically the communication, so when you're a data analyst interacting with a database, effectively the only thing you ever do is send select queries. And so Google's BigQuery, while it's not a relational database, allows you to send select queries. So I think select queries in SQL are sort of emerging as a de facto standard for communicating with data storage. So it might not be a traditional database, but it still understands SQL. That's sort of the lingua franca. And so because BigQuery understands SQL, basically generating the SQL for BigQuery is relatively straightforward. So I also have another package that's called BigRQuery, and all that does is interface to BigQuery that allows you to send arbitrary SQL and hit all the regular API endpoints.
And does it include the window functions?
And it includes those window functions, yes. Yeah.
For the window functions with MySQL, does it just write a derived query?
So it just gives up. If you can, so if a database doesn't support window functions, it is possible sometimes to work around it with subqueries and joins and so on, but decided that was too complicated.
No worries.
Yeah.
You think about using a standard SQL interface so that you get all the SQL speaking databases in place, like
Yes, I did indeed think about that. It's currently not possible because all of the SQL speaking packages speak SQL a little bit differently. I have, however, taken over maintainership of the DBI package and have been trying to prod the R database maintainers to modernize a little bit. The DBI interface was designed pretty much on 20 years ago. So there are a lot of things we now know about how you should interact with databases that were not known then. And I hope that we can sort of push R's databases connections to be a little bit more modern. But that is something, as the author of dplyr, I would love to be able to say. I don't have to write any specific code for different databases. But so for example, currently, if you have MySQL, PostgreSQL, and SQLite all loaded simultaneously, they don't work. But you can load any 2 out of the 3 and they do work. So it's basically a little bit of a nightmare working with multiple databases in R currently, but hopefully that will get better over time.
You know, it's really nice that you can interface to all these databases without the user having to worry about them. But it seems like they're also your weakest link in the future, that they're going to be the most constraining in getting more speed.
Yeah, so the databases are kind of, so my take on that is basically that's their problem to worry about, not mine. I think that we're also seeing some interesting research in databases. I think like BlinkDB is really interesting. How many of you have heard of BlinkDB? So BlinkDB is really cool because you write a regular SQL query, but you also say, I only care about the answer accurate to this much error. And so because you've given it an error bound, it doesn't have to look at every single row. It can use sophisticated sampling strategies and get you your result much, much faster. So I think that's really cool. There's like PrestoDB from Facebook, Redshift, AWS Redshift is really cool, and there's lots of other stuff. But by and large, I think they're all going to speak SQL, and I can speak SQL to them.
No, but I actually was referring to something else because you're talking about stringing together different operations.
Mm-hmm.
But so for each operation, you have a different pass in the data.
Oh no, sorry, I should have mentioned that. It's all done lazily, so it'll only ever send one query. So this sequence of operations here, for example, never actually hits the database because I never asked for the data. So it does things lazily. It builds up a definition of the thing you're trying to answer, and only sends it when you ask for the data. And it always hits the database for the minimal possible amount of data. Yep.
What's the best way to diagnose slow running queries?
I have no idea. Hire a DBA.
So I use the parallels true a lot in BDPly, so I guess now it's faster, maybe not as necessary anymore.
Yeah, so first of all, it's like, in the worst possible case, dplyr is like 100 times faster. So unless you're at 100 cores, you're still going to be better off. In the next year, I hope. So I should have mentioned the reason why it's so fast is I've been working with Romain Francois, who's one of the RCBP authors, and he's been writing really good C++ code. I hope by the end of the next year, that will all also be automatically parallel, so you wouldn't even have to worry about it. It'll just use all of the cores, or as many of the cores as you want, and should be then, 2 or 3 times faster. Okay, so Joe, are you ready to go?
You know why I need to follow you. All right. Hi, my name is Joe, the author of the Shiny package. How many of you here have heard about Shiny? Oh my god, okay. I forgot what city I was in. How many of you have actually written one or more Shiny applications? Oh, wow, okay. So I hope that whether you've written a Shiny application or not, you'll get a little bit something out of this talk, but definitely feel free if you have questions along the way, let me know. So what is Shiny? Shiny gives you interactive web applications around your R analysis. I think it's pretty important to highlight that Shiny is not a general purpose web application platform. You're not going to use it to replace Rails or Django You're not going to probably make your corporate website out of it. It's specifically to help our programmers or our analysts to create web applications that take their analysis and service it in a web browser. There's zero HTML, CSS, and JavaScript knowledge required. I'll show you the first one of my examples uses none at all. But if you do have HTML, CSS, and JavaScript skills, you will not need to feel constrained by Shiny. You're able to completely go to town with your Shiny apps. And I will show you an example of that as well. Shiny comes with a modern web UI style with attractive defaults. By modern web UI, it's not so modern anymore, but in the old days, you'd have inputs. You'd hit a submit button, and the browser icon would spin, and then the page would refresh and you get your results. And up until recently, that's how a lot of these attempts at making web applications with R turned out. And with Shiny, it's a much more contemporary feel, where as you change your inputs, the outputs recalculate on the fly. And attractive defaults, meaning out of the box you get the Twitter Bootstrap framework by default. So everything looks at least reasonable. You don't need to be embarrassed to show your colleagues or your boss. And if you want to customize that with HTML, CSS, and stuff like that, you're free to do that. It's designed to integrate with existing JavaScript libraries. It's really exciting what's happening in the JavaScript space with visualization, and a lot of the questions that we were getting from people who are using RStudio that we talked to, a lot of them were asking, how can we take all this amazing stuff that's happening in JavaScript land and take advantage of it from R? And that was a really difficult question for us to answer. So Shiny is our answer to that question, and I'll show you that as well. And finally, it uses a reactive programming model, which allows dramatically simpler code than traditional UI or web programming. My background's not in stats at all, as will become clear as I attempt to talk about k-means clustering. And my background's mostly in web development with a few years of desktop application development. And what you're able to do with Shiny is dramatically more terse, robust, and efficient than any framework I've worked in before because of this reactive programming model, which I can't take credit for, as a lot of it's inspired by Meteor.js and a lot of other interesting stuff happening in different frameworks these days. Okay. There are two main things that I want to convince you of tonight, especially if you have not played with Shiny before. Number one is that it really is quite easy. It's not an exaggeration. So let me show you a simple demo of a Shiny app. Okay. That's interesting. An overscan problem. Okay. Can you guys see that okay back there? Okay.
Ah, the good old Iris data set.
Yes, the good old Iris data set. So we've got an extremely simple application here that has oh, this screen is anti-glare. Okay. So we've got the ability to select what variable we want on the x-axis, what variable on the y-axis, and the number of clusters we want to use, and we're going to run k-means clustering on it. So the x's here represent where the cluster centers are, and the colors represent the membership to a certain cluster. So you can see here, as I change these variables, the plot updates right away. And then as I change the number of clusters, you can see those clusters move. So you can use this to try to figure out the best number of clusters. Okay, so let me show you the code behind this. If you have used Shiny before, you may not, well, I assume you have not seen this particular view before. This is a feature we're working on called Showcase Mode, where you can take any Shiny app and run it with the flag showcase equals true, and it'll actually show the code side by side with the actual application. And in this particular case, it's not a lot of code. So every Shiny app, or almost every Shiny app, has two files. There's UI.R and there's server.R. The UI, as you might guess, is used to define what the user interface of your application is going to look like. And that's it. You don't do any analysis here. And server.R is going to be where you're actually doing your plotting and doing your subsetting and what have you. So let's just take a quick look at this. In this particular case, this user interface, I've got, at the top here, I've got a title. On the side here, I've got a sidebar that contains 3 controls. Sorry about that. And then here, we've got this output area where right now we've got one plot output, but you could have any number of things and any number of different types of things there. So you can see, looking at this UI code, there's no HTML, there's no JavaScript.
Joe, can you make it a little bigger?
Oh, sure.
Because it's almost there, but we can't really from here.
Is that better?
Yeah.
Okay.
Thanks.
The first thing here is Shiny UI, and this is just boilerplate where you're telling Shiny what I'm about to pass to you, I want you to use it as a user interface. Page with sidebar is just a template that we've written. This was the first sort of template that we included with Shiny, and sadly it was the last one until last week. We've got a bunch more now.
I'm sorry, where is this code located? Is it in HTML? Is it in the web page? Is it in where is it?
Oh, yeah.
This fraction of code, this section of code.
I have made it a little bit too magic. There is, every Shiny application has its own directory on disk. And inside of that directory, I don't know what, I have a bunch of garbage in here, but it's just server.r and UI.r inside of a folder, and that's where those live. And when you run a Shiny app, you point it at the folder and say, this is the application I want to run, and it goes and looks for UI.r and server.r for you. Yeah, sorry, this stuff is all covered in the tutorial. I'm sort of hand-waving around some of the setup.
I think he might have been asking about server versus client. What's running where?
Oh, yes, okay. Let me get back to that in 1 second. That's a really great question. So there's page with sidebar here, and this page with sidebar contains 3 subpanels. There's header, sidebar, and main, and that corresponds to, this is the header, this is the sidebar that has a gray background, and then the main panel. And inside of the sidebar, we've got a select input, a second select input, and a numeric input. And inside of the main panel, we've got a plot output. So you can see there's a very direct one-to-one mapping here. There's nothing too mysterious about this. The one thing to notice here is that the select inputs and the numeric input and the plot output, they each take the string as their first argument. That's the identifier for that input or output. And we're going to need to refer back to those identifiers when we start writing our R code that want to look at those inputs and generate outputs. Okay. So in answer to the gentleman's question about where this code runs, well, it runs on the server. There's no case in which there's actually R code running in the browser. There's some other projects that are trying to do that. That's not our take on things. But it turns out that all this is an HTML generation function. So in fact, I can even just I think I can just type it in to RStudio. Okay, well, it's escaped, but you can see that that's literally just generating HTML. So if you speak HTML, you can also directly inline HTML code here if you want to. You can include an HTML file that you have on disk, so you can use your favorite HTML editor, whatever you want to do. Any questions on the UI.R before I move on to the other side? Okay. So server.R, you can see, is also not a whole lot of code. We've got 3 main things that are happening here. We've got 2 calculated values, essentially, and then we've got this code that that draws a plot. Okay. So the first calculated value I have is the selected data, and that's just the name I call this variable. There's nothing magical about selected data in Shiny. I just made a variable that has a calculated value that takes the iris data set and selects out the columns that the user selected in the sidebar there. So you can see input $xcall. Xcall is what we call that first select input. And input $ycall. Ycall is what we call the second one. So those values are automatically replaced with whatever the user selected. And keep in mind, this code is running on your server. So we take care of shuttling the values back and forth between the browser and the server. And the fact that that reactive keyword is there, this is the reactive programming I was talking about. What that means is that selected data, anytime you ask it its value, it will return to you the current value with respect to what the user selected. So as that value changes, it will always tell you the right answer. But it won't calculate any more often than it needs to. So if the value that the user hasn't changed, if the values that the user selected have not changed, then it will not re-execute. It'll just give you the same value that it had last time. So it's smart enough to hold on to its values and know when those values need to be refreshed. Okay. This second calculated value does the k-means clustering calculation. You can see here that it uses this selected data calculated value, and you call it like a function in order to retrieve its value. And this one is referring to the other input that we have, the text box here that has a cluster count. And then finally, this render plot here is being assigned to plot1, which is what we called that plot output in the UI. And you can see here, like, this is just typical R plotting code. There's nothing mysterious about this. You're just setting some margins, doing the plot using our two calculated values, and then drawing the points for the actual cluster centers. Okay.
Sure. Why separate UI and server.r? Because it seems like you're tying some R code on server.r to oftentimes the control on UI.r, and it seems like you're building a pattern of developing where you're switching back between the two.
Yeah.
And it's easy to get out of sync.
Yeah, it's true.
What was the philosophy behind like separating, or do they execute at different times? Or?
They do execute at quite different times, and I think at the time that I did this, I was thinking ahead to a time where people would be deploying these things on servers on the open internet. And what happens is UI.R, that UI only needs to be calculated once, and then it can be cached forever. It's the same HTML that's being returned to everyone. So I thought that there might be a time where you have a fleet of servers that serve up the front ends, and then a fleet of servers that do the back end calculation. And I think, given that I didn't think it was that big of a deal to have two separate files, and in fact, aesthetically, I think you could make an argument it's nice to have that separation of concerns. I thought, on balance, that two was better than one. That being said, there's another way to use Shiny where you can have everything in one file. I can show you that in a little bit. So one interesting feature of this showcase mode is that as I change these values here, you can actually see highlighted in yellow on the right what code is executing. Okay. So in this case, I'm changing the x variable, and you can see that all three things need to re-execute, right? The selected data obviously needs to change because I'm selecting different data. The clusters need to be re-executed because they're dependent on the selected data, and then the plot is dependent on both. So if you change one, they all have to change.
Does it know what is changed in this case, or all of the reactive functions get called again whenever something changes?
Great question. Well, let's try the cluster count. So selected data doesn't use the cluster count, so you'd think that it wouldn't need to execute, and indeed it doesn't. Okay, it's not obvious, but when you change the width of the browser, we actually need to redraw the plot to match the new width of your window. Yeah, okay. And you can see there that, again, the clusters don't need to re-execute, but the plot does need to re-execute. So, I mean, especially if you have a little bit of computer science background, this is where you call BS, right? Like, how does this know what exactly its dependencies are, and is that something that you can actually rely on, and does it really work? And the answer is it's actually extremely simple and very robust. If you basically have to follow a few certain rules. I'm not going to get into that right now. If we have time at the end, I'll come back into how this is implemented, and some of that is talked about in our tutorial online, or come find me afterwards. I'm happy to continue explaining. Okay, so any questions about this app before I move on? Okay, so you can see here, we're talking about, what is this, 35 lines of code to generate a reasonable looking, very simple app. And I think if you were to look at some of the Shiny apps that you might see, on Twitter that people pass around, you might conclude, or looking at what's shown in our tutorials, you might conclude that pretty much all Shiny apps kind of look like that, and that they all do sort of the same thing. And the truth is that we're all really just scratching the surface right now of what Shiny is capable of doing even today. So I've written another demo that shows at least a little bit more of how deep the rabbit hole goes with Shiny. So there was a Super Zips. There's an article called Super Zips that was written, that's published by the Washington Post maybe a couple weeks ago. Did you guys see this article about Super Zips? Super zip codes, basically. So it's saying if you analyze the average level of college education and the median household income for a particular zip code, and then rank all the zip codes in the United States and take the top 5% by those measures. Those are sort of these elite super zip codes where the schools are better, they're safer, people are happier, they're just better people, right? I mean, like, no. I mean, the article went into some interesting investigations into the ramifications of the existence of these zip codes, the fact that they cluster together in around metropolitan areas, and you might have kids who grow up their whole lives only knowing people from these super zips, and what does that mean for us as a society, and
Please take away the statistics license of the social scientists.
So what this is I took some of that same an older version of that researcher's data set was online, so I decided to throw it into this interactive explorer. By the way, the Washington Post, they published this as an interactive visualization, and it's actually, it's based on some of the same JavaScript libraries. They did quite a great job, and I was really interested in seeing what kind of similar things we could do in Shiny in a limited amount of time in code. So here we're looking at the United States. There are a lot of red dots and a very few number of blue dots here. On the right, I can choose what variable to map to the color. So right now it's a binary question of, is it a super zip or not? Yes is blue, no is red. I'm colorblind, so I'm told it's blue and not some other color. Centile score basically maps the centile score for that particular zip code to a color ranging from red through yellow to blue, or you can rank it by any of these other measures. And then the size right now of each circle is mapped to population. So let me come in a little closer here. You can see here that, no surprise, around San Francisco there are a bunch of super zips. This is broken right now for some reason, but when I click it, it's supposed to pop up with a bubble that shows the zip code, city name, and the relevant statistics for that city. It's kind of bummer. Anyway, on the right here, you can see that I've selected the top 5 percentile. Top 5 percentile? However,
Top 5%.
Top 5%. Well, it's okay. Anyway, the top 5, whatever unit, of zip codes are classified as super zip, and that's what this researcher Charles Murray said in his definition. But we could change that to, let's say, 20, and just see now what zip codes fall into that category. Oh, there's actually not that much difference. Or it's doing something else now. Okay, there we go. So you can see that now there's way more. So there may be some communities here that are sort of on the brink. You can see here on the right there is a histogram. That is a histogram of just what's visible inside of my browser window right now. Mm-hmm. So this is specific to the San Francisco Bay Area. I can move over to, well, first of all, look over to the right here. You can see that there are quite a few super zips, and yet there are also some that are at the very, very bottom of the scale. Mm-hmm. I think that's not a huge surprise if you look around here, right? If you go to Nevada, things are not looking as happy. And I think you'll find that there are big swaths of the country where there are no super zips at all. Like I don't think there's one in Wyoming, for example. You can see that's quite negative there. But move over to the to the northeast corridor here.
$100.
And sorry, what's that?
It's only something like that when they compare money in different parts of the United States. But renting a house in the Bay Area, it's a shack is $1,000.
Yeah.
In Wyoming, a mansion is $100.
Right, right. So we could compare it just by education level, and I think you'll find that it's similarly. Yeah, you can see here that the eastern seaboard. Well, I changed it to 20, but still, any way you slice it, New York, Boston, Washington are just lousy with these things. Okay, and then at the bottom here, you have a scatter plot of the college level of college. Sorry, percent of adults over 25 who have at least a BA, and then on the y-axis, the median household income. So, and the scales here are set to the national bounds. So as you move around the country, the scales stay consistent, but just the data points kind of come and go. As you can see here, how they fit in with the rest of the country. Okay. Is there anything else I want to talk about here? Okay. So this is using a library called Leaflet. It's essentially an open source clone of Google Maps, and it's really excellent. I took some time a few months ago to write a binding for Shiny for Leaflet. So if you are an R developer and you want to drop a Leaflet map into your Shiny application, you can do that with just R and really a pretty minimal amount of R, as I'll show you in a moment. Whereas before you'd have to learn JavaScript basically and then figure out how to connect that up with R. So compared to the k-means example, there's a bit more here, but you might be surprised that it's not all that much more. Can you guys still read this back there? The code? It's a little small. Okay. Yeah. So here's the UI. I can't show you both at the same time, unfortunately, but here we just have some choices that will appear in those drop-downs for what you want to appear to correspond with the color and the size. Shiny. Oh, killed it. That's what happens when Shiny apps die. We have some CSS and JavaScript here. So I added a little bit of CSS to get the control box to look the way I wanted to with the right fonts and stuff like that. So just a little bit there. The Zip Explorer control panel here is draggable. That's using a library called jQuery. So these two lines initialize jQuery. And then here's my leaflet map. So just like any other input or output, I give it an ID. So I'm going to refer to it from server.r as map. And then the rest is just leaflet options about where you want this map to appear, what kind of geographic tiles it should display. And then here, this column here, this is my, my control box that lets you choose the color, the size, and then the input. There's a number input here that's contained inside of a conditional panel. And what that does is this super zip threshold control can come and go as needed. So if I'm not selecting based on super zip, then I don't have to ask that question and it can go away. So that's a conditional panel. And then just my two plots, centile and the scatter plot. And then I just have the citation for where the data came from at the bottom. I'm not going to go into every line of the server code, but it's all, like 90% of it is just R code that you're used to writing today. I'm reading an RDS file, which you now know about thanks to Hadley. I'm doing some very straightforward manipulation of this data frame. Doing some sampling, because leaflet can only handle so much. And then I'm creating a leaflet map to correspond with the map object I have in the UI. And everything else is sort of what you'd expect. I need to do some calculations on zip codes that are currently visible. So I do that using normal, range and subset. I'm doing, I don't know, plotting. Oh, here's a histogram. So I hope it's obvious that this is all very straightforward R analysis that you're probably used to doing today with a pretty small amount of boilerplate around it to hook it into this Shiny application. So yeah, this is the feature that didn't work, where if you click one of those circles, it's supposed to run this code that puts together, it's creating some HTML to display in a bubble that pops up right there, but it's not working right now. So, sorry, did someone have a question? Okay, so that's it for that example. If you'd like to get started with Shiny, Google Shiny tutorial. Even if you're not the kind of person that normally reads tutorials, this is a good one to read. Shiny's not the kind of thing that you can just sort of look at the help and figure out how to get started. You do need to know how to get on the right path. If you are someone who's been into Shiny for a while, I thought I would just mention some of the things that are new. You can return values from Shiny applications right now, and what does that mean? So this is the last demo I have for you. So up till now, I've shown Shiny apps being sort of these standalone apps that run in a web browser. You can launch them from your R session, but they're really these sort of fire and forget kind of things that you look at this Shiny app in a browser, and then you close it and you go back to doing whatever you were doing. It's also possible now, and this is sort of I don't think I ever got your name, but talking about having both things together in one page. So if you use Shiny, you can use Shiny as something that you run from an existing body of R code. Like, let's say that you want to do some analysis, and in the middle of that, you want to ask the user a question, and maybe it's something that's more complicated than a simple yes/no. You might have used identifier or locator to do some simple versions of this in the past. Well, you can use Shiny to do more advanced versions of this now. So in this example, instead of having a server.r and a UI.r file on disk somewhere, I just have my UI and server inline, and I pass them into a Shiny run app function call. And there's a new feature of RStudio 0.98 that will let you say, I want to show this Shiny app directly inside of my IDE. So in this case, I created a cutoff function that, I'll just show you, it's easier for you to just see. So I'm going to run cutoff, and I'm going to pass in empty cars and tell it I want to run on the weight and miles per gallon. Okay. So, oh my. Okay. So there's empty cars, weight, miles per gallon. I can click on this plot, and it will draw a vertical line where I clicked, and everything to the left is highlighted now. And if I'm happy with that selection, I can hit select. Let me make it smaller. And these rows will be returned to whatever called it. In this case, it's dumped in the console. You could certainly imagine, if it's a knitter, you might want to check your data after some number of steps to make sure that everything's sane, or maybe you want to provide some supervision to your machine learning thing. I don't know. And this is something that was not possible with Shiny a few months ago, but it's possible now.
Joe, it's a similar thing. How do you get the boundaries of the map in the previous application, so that so when people zoom in and out of say California, the statistics have to change right on the right. So how do you get that rectangle?
How do I get the bounds?
The boundary.
And okay, so in the particular example of leaflet, for that map, the bounds of a particular map are given to you as one of those inputs that I showed you. You have input $, X call, Y call. In this case, when you make a leaflet map, it gives you map_bounds. Or whatever if you call it foo, then it's foo_bounds. And that is an always up-to-date list of top, left, right, and bottom coordinates. And it's a similar thing with what I just showed you. Clicking on this. Here I have a input $cutoff, where up here, when I made the plot, I said click ID equals cutoff. I don't know if you can. Click ID equals cutoff. That means capture the clicks and stick them in the ID, the input ID called cutoff. So now you can just treat that as another reactive value, and everything just works. So again, there's no click handler here. There's nothing here that says, oh, when a click happens, do this. All that happens is when you're rendering the plot, if there's a cutoff, then use it, and this thing will re-update if you do change that, the existence of that or not. So, does that answer your question, Antonio? Okay.
So when you're getting the click like that, are you just does that just end up being a call to the locator, or do you have other ways of figuring out where the user clicked on the plot?
Yeah, we cannot use locator because that works directly on a graphics device, and since we're in a web browser, there is no graphics device. It's long gone by the time you see it. So what we basically do is we save, at the time that we make the plot, we kind of reach in and grab the user coordinates that give us enough data to do that transformation ourselves. So we can basically do what locator does, but we happen to do it in JavaScript. And that's none of your concern, it all happens behind the scenes. So it's subject to the same limitations as locator is. For example, unfortunately doesn't work with ggplot and anything else that uses grid graphics, which is a serious limitation. The good news is item, oh, it's not on here. On the next slide, I'll talk about the next version of ggplot is going to be very well suited to this generation of applications. Instead of just doing static plots, you'll have interactive plots that work really well with Shiny. Yes?
So does it ship with a web server as well? I would imagine you need one.
Yes. There are a couple answers to that question. It ships with its own web server called HTTP UV. It's a package that's on CRAN. It essentially uses the same web server technology that's in Node.js. We just wrapped it up in R. We basically use that as a development server. We don't recommend that you run it in production or even for a work group. For that, if you want to run on your own machine for yourself, just use Shiny Run App, and under the covers they use HTTP UV. If you want to deploy Shiny apps, you need to use Shiny Server. There are open source and commercial versions of Shiny Server now. Shiny Server works great, but the open source version works great, but there's no authentication, and it can only use one R process per application, which actually ends up being fine for a lot of applications. But if you're doing simulations or something, you're going to want to load balance across multiple R processes. This is all stuff that, if you really get into Shiny, you will run into these problems and know whether or not you need to run on Shiny Server. You'll know whether or not you need to run Shiny Server Pro. All that stuff is explained on our website at RStudio.com. So error handling and debugging was kind of a sore point for us with all this interactive stuff. All this reactive programming. Things happen sort of outside of your control sometimes, and it's hard to know when you get an error what code caused it. So our error handling tools, especially in conjunction with RStudio, are way better now. You can get interactive, step-by-step debugging when you hit an error in Shiny, things like that. So we support data tables now, which is a way of displaying tabular data that's somewhat interactive. So instead of just having an HTML table, we've got this sortable, and you can search, and there's paging. And this is real server-side paging, so even if you have, a million rows or something like that, it'll only, pump to the browser the subset that you're looking at. So you can use this to expose very large data sets through Shiny. We've got a reactivity visualization tool. So those of you who are really gotten into Shiny and written some complicated applications, this is very cool. Almost like show-off technology, that basically all these relationships that are implicitly created as you write reactive code, we can visualize it as a D3 visualization right from within your web browser. So when you're using your Shiny app, you hit Control F3, and it launches another browser tab that has a interactive visualization of the code that's running and the relationships between the different chunks of code. So I mentioned before that our page with sidebar, that's how most Shiny apps look right now. Just in the last week, a ton of new stuff has gone in here. That's the old page with sidebar again. But there are new ways to lay out pages. You can do arbitrary grid-based layouts. There's a nav bar-based layout now. You can do menus. All this stuff that was really pretty low-hanging fruit. We just never got around to getting on top of it. You can also swap in arbitrary bootstrap themes with a single line of code. So yeah, you can see here there's a reference to there's lots of free themes that you can grab and make your app look more like that. We had some problems with RStudio server, embarrassingly. Now it works really well with RStudio server. Shiny server has been out in open source for a while. Now there's a professional edition. And shinyapps.io is Shiny app hosting in the cloud that we, RStudio, provide. It's in beta right now. If you're interested, you can go to shinyapps.io. The way it works is, right from within RStudio or wherever, however you use R, you can type deploy app, and it will bundle up that directory, publish it to a new instance that it stands up in the cloud. And right now it's free, but eventually we'll probably need to start charging for some set of that stuff. So really quickly, what's next for us? We're working on, we think we have a pretty good tutorial right now, but we're working on making it even better. More examples that illustrate some of the new things that we've added, which we've been pretty short on doing. There's some really exciting stuff that that Hadley and Winston Cheng of ggplot fame have been working on for doing interactive graphics in the spirit of ggplot. I'm sure we'll be back sometime in 2014 to talk about that. And more built-in widgets right from within Shiny, and showing progress and errors, all things that we want to work on, as well as beefing up our reactive system to make it even more powerful. So. Okay. Any questions?
Can it run from a local file?
What is that?
Like I don't have a server. I'm just running it locally.
Yeah, it cannot. That is a fundamental. I think there are a lot of things in Shiny where I can say it doesn't work that way, but it certainly could.
That is localhost.
That is yeah, localhost is fine. That's how it runs by default. So what we absolutely cannot do is build a Shiny app and export it to just a plain HTML file that you can throw on a cheap web host somewhere and not have R anywhere in the picture. That's fundamentally not how it works. There's a project called ClickMe by a guy named Nacho Caballero or something like that. That is more in that spirit. Along with, if you're specifically after one or two charts, there's a project called RCharts that's on GitHub by Ramnath. I'm not even going to try his last name. An amazing. He's doing some really interesting things with JavaScript and R with and without Shiny, and his RCharts package has a capability of outputting plain HTML. But Shiny is fundamentally about having R at runtime. And yes, now you have to run a server, but the advantages are you can hook up to a live database. You can run real-time analytics dashboards that just stay up on a TV, and you don't have to drop to some other language to do that. You can just do that all from within R. So yeah, that's our bet.
Panning, zooming, sliders.
Yeah, so sliders are built right in, just slider input. Panning and zooming, I think really that's sort of a property of the particular visualization that you're looking at. So that's obviously quite easy to do with Leaflet. It's built in. How you would do that with a ggplot, I mean, I think it's possible, but it's not something that you just drop down and do. I think it's more likely that ggviz will, the next version of ggplot will make it much easier to do that kind of thing. In addition to all the other things you'd expect an interactive plot in 2014 to do. Yeah.
So you use WebSockets?
Yes, so WebSockets, if you guys aren't familiar, it's a relatively recent browser technology that now all the modern, all the browsers ship it. That basically lets you set up a direct connection between the client and the server, or the browser and the web server that stays alive, and you can push messages either way. So yes, if you run Shiny from your desktop, it uses WebSockets. If you run it through Shiny Server, it actually uses a library called sock.js that emulates WebSockets. it'll use WebSockets if they're available. If you're running on IE 8 or 9, for example, or your firewall blocks WebSockets, then it will fall back to other things that approximate WebSockets. And that's actually really, really important for real-world deployment.
So the Shiny Server Pro, that takes care of the authentication then to lock down sort of access to data?
We hope it does. It's really new. I mean, I think we just opened it up for beta, a week and a half ago or something like that. So people are just starting to use the authentication part for real. Right now we support sort of a flat file-based authentication where you keep a separate store for Shiny Server credentials. We also support Active Directory and LDAP. So if your organization already has authentication storage working that way, in theory, we just are plug and play. But again, it's barely been tested so far. Yes?
From what you've described so far in this presentation, it looks like Shiny is oriented towards doing essentially a single page application. What happens if you want to have multiple Shiny graphs embedded in some existing web application? How do you go about doing that?
Yeah. So that's funny. I thought your question was going to go a different way, which is, what if you have an application that spans multiple pages, like a multi-step process or something like that? So I'll answer both questions. For sure, the vast majority of what people are doing with Shiny are, the page is a Shiny app and it's nothing else. But Shiny was always intended to also work in the scenarios where you primarily have, your whatever content you would normally put on a web page, and part of it is lit up with Shiny. So it certainly works that way. We don't do a lot of documentation around it because it's not a super common use case, but it certainly has been done. People are doing it. I think that there's. I don't know if I'm going to be able to find. I could have sworn that this. Build a model, maybe? Oh, well, these guys are just running in an iframe or something. Oh, no, that's scripty. These guys have done it, so it's certainly possible. The question I thought you were going to ask is, what happens if you have an application that you want to span multiple pages? We just don't support that very well right now. It is very much a single-page app framework. That said, people have worked around this by having, for example, things that look like you're changing pages, but the URL never changes, right? Like you click next and all the UI disappears and new UI comes up. That's actually fairly straightforward to do in Shiny, although obviously not as nice as if we fully supported multi-page. That's certainly something that's possible that we'll do in the future.
I was just curious, what do you see people using Shiny for mostly now? Is it for displaying results of things, or just putting design on the domain?
Yeah, boy, what don't they use it for? Well, actually, a bunch of you raised your hands and said that you've at least tried Shiny. Anyone want to volunteer what they were either using or thinking about using Shiny for? That's actually it's a risky tactic for me to take. Yes. Well, okay. For example, I was shocked to find out that the bioconductor community is really hot on Shiny. Genomic analysis and microarray visualization or whatever. They often find themselves in the situation where they have more data than they can fit on one page, and you really need to do a lot of sort of digging around. And often the people who are doing the digging are not the people who are writing the R code. So the statistician who can write the R code to generate the output, they can't look at a plot and tell you the scientific or biological significance of what they're seeing. So they'll collaborate with a scientist, and Shiny has become for some of them the interface by which they do that. It's really helpful. People are definitely using it a lot in teaching. So if they have some kind of statistical method that they're trying to get the point across, k-means clustering, for example. Usually when you see tutorials, you see just 8 plots. Like first we do this, and then watch if we change this is what happens. To be able to put the controls in the user's hands and say play, and you come to your own conclusions, we think is really powerful. People are using it for financial reporting, both sort of internal how are we doing kind of metrics. I think that's really common. as well as using it to actually analyze financial models and see if, look for arbitrage opportunities. There are some guys that are working on Bitcoin arbitrage tools using Shiny. So it's really all sorts of things. Yeah.
Just to answer your question, I work at Sacramento State doing educational data mining, and I built a very simple Shiny app just to make sure I could do it, but what I'd like to do is build a dashboard that our administrators can use to understand how our students are doing with drillable tables and graphics and those kinds of things. But of course, I just have to learn more about Shiny before I can do that.
Absolutely, yeah.
I've been using Shiny Apps.io, but I'm building these apps from flat files. Is there a way to connect to a database just using like deploy app?
Yeah, with deploy app, right now with Shiny.io, we don't offer a database service. So that means that you can connect to any database that's available from the machine we haven't hosted on. Which, if you can handle the security implications of that, then great. I think we'd certainly like to eventually offer, something like Redshift or whatever, or RDS as an out-of-the-box option for sure. But for right now, it's a little bit of the Wild West on Shiny Apps.io.
Yeah,
it's quite beta, if you hadn't noticed, or alpha. I think we don't even call it a beta.
So I have one question about the back integration into the UI. So I work in genomics, so you have a lot of gene lists, right? So first of all, the type ahead type box. Here you have 20,000 possible inputs, but nothing else.
Yeah.
Some kind of type would be nice, but also for subsets of the inputs makes sense, right? So you first select a subset, and then the second select box should be dynamically updated based on what is available. I
Yeah.
don't know if that back integration is possible.
Yes. Now you can tell that I'm not a data scientist because it wasn't possible in the first version of Shiny, or at least it was possible, but using this sort of reactive UI technique that is a little bit heavy-handed. So I think there are two parts to your question. Number one, what happens when you want to type in, say a gene out of many thousands of possibilities? Right now, what comes? Really? Okay. Sorry about that. Right now, we have these select boxes that obviously don't scale. Hopefully by the first week of January, we will have integration with Select2, which is a JavaScript widget that that is just really beautifully solves this problem. There are demos that I can't find right now where this already works with Shiny, but I can start typing here and it'll do searching and all sorts of fun stuff. You can do multi-selects and stuff with this. The other question is, once you've selected one of these values, perhaps that influences some of your other possibilities. And yes, there are a whole new set of functions. So if you have, let's say, another select input that needs to change, there's a function called update select input that you can call from server.r. So in server.r, you would call update select input with a new set of choices for those other controls. So you can dynamically change them that way. You can also make them come and go using conditional panels, using reactive UI. So there are a bunch of tools.
You do that in the server.r.
In server.r, that's right. As all the runtime stuff has to happen in server.r. Yeah. If you have any questions about that and have trouble figuring it out on your own, definitely ping us on Shiny Discuss. We've got a very vibrant discussion community or discussion group at Shiny Discuss. If you just Google for Shiny Discuss, you'll find it. There's something like 1,500 members now, and the traffic is such that I can't even attempt to answer them all anymore. But there are enough people around, and that is a very common question. So I think you're likely to get some play on that. So, great. Any other questions?